An ice cube slides down a ramp that makes an angle of 18 degrees with the horizontal. What is the acceleration of the cube? Assume there's no friction between the ramp and the cube. So it's a relatively simple problem, but having it at an angle on the ramp makes things a little confusing. Let's look at the forces on the ice cube. I'm going to go ahead and draw them right on the picture here. We have gravity. Ooh, I need a pen. We have gravity pulling straight down, and we have normal force. And remember, the normal force has to be perpendicular or normal to the surface. Those are the only two forces we have. There's no friction, there's nothing pulling on it or pushing, there's no tension, just the two forces. The normal force is perpendicular to the ramp, so it's not pushing it up the ramp or down the ramp. Gravity is pulling it slightly down the ramp and also into the ramp. So this is the tricky part. Since the motion is along the ramp, we want to look at the forces along the ramp and the forces perpendicular to the ramp. So instead of looking at x components and y components, we're going to look at parallel components and perpendicular components. So I'm going to draw a line like that. That is the component of the force that's pushing, of the gravity that's pushing the block into the ramp. And then there's another force like this that's pulling, that's the part of the gravity that's pulling it down the ramp. Notice this is a right triangle with gravity as its hypotenuse. These are two components of the gravity vector. We also need to know what this angle is. If we look carefully and remember our geometry, this is a right angle because mg is straight down. So this angle, and this angle have to add up to 90. So this is 90 minus 18. And this angle have to add up to 90. So this will be 18 degrees. So now I'm going to look at the perpendicular component and the parallel. This one I can write as mg cosine theta. This part, this little part here, mg sine, I don't need parentheses, mg sine theta. So if we look at the net force, mg cosine theta and the normal force, those just cancel each other out. The force that's pulling it down the hill is just this part, mg sine theta. So we're going to just look at the forces, instead of saying x and y, perpendicular and parallel. The perpendicular forces we have normal minus mg cosine theta equals the acceleration in this direction, which is 0. So the normal force equals mg cosine theta. But that's not actually going to help us very much. Let's look at the forces parallel. We've got just this mg sine theta. mg sine theta equals ma. And if we divide by m, the m's cancel. So a is just g sine theta. And that gives us 3.1 meters per second squared. Notice if sine theta was 0, the ramp would be flat, and sine of 0 is 0, so the acceleration would be 0. That's not surprising. If it was just on a flat table, it wouldn't be accelerating down a ramp. If theta was 90 degrees, it would be all the way vertical. Sine theta is 1, so the acceleration would just be the free fall acceleration, g. there's another way to look at this. We could take this whole problem and turn it on its side. Well, sort of on its side. If I rotate the whole thing, you could just rotate your paper. It would look like this. The normal force is straight up, and mg is down and off to the side. So we could draw, this would again be theta, 18 degrees. This would be mg cosine theta, and this part here would be mg sine theta. So we could say, now we've got vertical and horizontal. Again, in the vertical, the normal force and mg cosine theta cancel. Horizontal, we've just got mg sine theta equals ma. And the m's cancel, and you get a equals g sine theta. Okay? Ramps are a little confusing. They're hard to visualize. But when you look at it, the math itself is not hard. So, we've got that. Let's go a little further. Now the ice cube rests on the ramp, and there's friction. So we've got these two forces, mg and normal force. Now we've also got friction, and that's pulling in the direction up the ramp. That's preventing it from sliding down. That's friction. So we're going to assume that the friction is at its maximum, so it is just barely prevented from sliding down the ramp. Again, we'll split this into the perpendicular and the parallel to the ramp. mg cosine theta, mg sine theta. Again, this is the angle, this is theta, and it equals 18 degrees. So we can say, if we say the friction well, let's write this out properly. In the direction parallel to the ramp, we've got friction minus mg sine theta equals the acceleration. Now it's at rest, so the acceleration is 0. So friction equals mg sine theta. Now let's look perpendicular to the ramp. Perpendicular. We've got normal force minus mg cosine theta equals the acceleration perpendicular, which is 0. So the normal force equals mg cosine theta. Now I'm trying to find the coefficient of friction, and the static friction is mu static times the normal force. So mu static is going to be the friction force over the normal force. The friction force I have down here. The friction force equals mg sine theta. The normal force from up here equals mg cosine theta. And you'll notice this simplifies quite a lot. The mg on the top and the mg on the bottom cancel. It doesn't depend on gravity. Sine theta over cosine theta, if you're a trig buff, you know is tan theta, which makes it a lot simpler. And tangent of theta equals, I don't want to plug it in my calculator, I'm going to look at my notes, 0.325. Because theta is 18 degrees.